So we spoke about Gram-Schmidt projections, etc. last time. What I am going to talk about today is the notion of adjoints. Of operators. Okay. So let me recall the familiar meaning of the word adjoint. So if you've got a matrix, for example, so if A is a matrix n cross n complex matrix, for instance, then what does the adjoint mean? What is A star? I mean, the word adjoint actually also has other meanings which come up in inverses, right? Computing inverses, but this is in the context of inner products. What is the adjoint of a matrix? Transpose conjugate, right? So that's our usual notion of adjoint. But this is in the context of matrices. Now, what I want to talk about is the notion in a slightly more abstract setting of linear operators from spaces. So observe, of course, linear operators and matrices are in some sense the same thing, and in some sense not quite. An operator can be converted into a matrix, but to do that you need a basis. So there is a choice involved in order to pass from operator to matrix. So what we now want to do is to somehow understand what adjoints are, not using matrices, not using bases, but sort of just at an abstract level. What is it at the level of operators? Okay, so let us begin with the setup. So we will again take V and this is a inner product, so it is a finite dimensional inner product space, and we can think of it as over real or complex numbers. So I mean I will kind of mention what happens to both situations. So the first thing here is that what is the inner product really? So let us think of the inner product as follows. It's sort of a gadget which takes two inputs, right? So an inner product, if you remember the way we said it, it's a function from V cross V to the field F, F being the underlying field which is real or complex. So in a sense it's a gadget which takes two inputs or two variables, with the property that if you fix the second variable and you let the first variable vary, so if I take V1 plus V2 but I fix the second guy to be W, then it varies linearly with respect to that, right? Or likewise if I put constants, then it comes out. Of course this will not happen if we fix the first variable, because if we are working over the complex numbers, for example, if you fix the first variable then you will not have linearity, but rather you will have conjugate linearity. So C will come out as C bar, that is the only thing which will happen over the complex numbers. Over the real numbers, of course it is alright, it is linear in whichever one you fix. Okay, so it is sort of bilinear or conjugate linear, and this sort of brings us to the relationship between inner products and the space V star. So recall what is V star, it is called the dual space of V, right? V star is just all linear functionals. So this is a space of all linear functionals, meaning linear transformations from V to the one dimensional vector space F itself. So these are your V stars. So if V is R2, for example, so let us say the vectors in R2 all look like x comma y. What is an example of a linear functional? So F acting on an element xy of R2, for example, let me write this. Is this a linear functional? 2x plus y? It is linear, right? Because if I change both x and y simultaneously, it will sort of vary linearly. Now here is the interesting thing, and this is also something, I mean we do it without thinking so much, also something which Pranabendu talked about. This 2x plus y can actually be thought of as 2 into x plus 1 into y, right. In other words, it is actually the inner product of x y with the pair with the vector 2 comma 1, correct. So, in a sense this linear functional is, there is a certain relation with the inner product, which is the following. This linear functional is obtained as follows: you fix the second component of the inner product to be that particular fellow 2 comma 1. So, you fix the second and then you vary the first, and when you do that, you know you will get something linear, right. And this linear functional happens to be the guy that you will get from the inner product when you fix the second component to be 2 comma 1. Okay, so that is our point of view. Inner products allow you to construct linear functionals in the following manner: you fix the second component to be whatever you want and let the first component vary, that will be a linear function always. Okay. Now, the important thing is that every linear functional is actually of this form. Okay. So, this is, let us maybe write it out formally. It is a very simple statement, but it is an important point of view. So, every linear functional, so given any f, V star, V is a finite dimensional inner product space, I can actually find a unique element, it is called V maybe, there is a unique V in V such that f of x, let me call it, equals xv for all xv. Okay. So, my linear functional can be obtained by just taking the second component of the inner product to be my vector small v. So, this is my vector v here. For example, in the thing that we just looked at, if my linear functional is this guy 2x plus y, then the v, the vector that we obtain from it, is just 2 comma 1. Right. Now, this is true in general, and I mean the proof is more or less obvious. No, for all x belongs to V. So, this is, so see, f of x is what I am calculating. Evaluating f at x will give me the same answer as taking inner product of x with my fixed vector V. Okay. So, let us just prove this. The proof is more or less straightforward. So, the way we will do it is to say, let us take an orthonormal basis, for example. So, let EI let this be an orthonormal basis of V. See, what is it that we want? This is the thing that we want, f of EI. So, if at all you are able to find that V, we know what property that V has to satisfy. We want V to satisfy this property. Right, because in particular if I take x here to be any of the EI's, that equation has to be satisfied. So, I know that this must be true, f of EI should be EI inner product V for all I, and so this determines V uniquely, right. Why? Because this tells me what the inner product of V with every EI is. So, I will just take conjugate on both sides, right. I am just going to switch the order. When I do that, in general it will become conjugation over the complex numbers. So, V inner product with every EI is nothing but f of EI bar, right, okay, and f is given to me, I know what my f is. So, this is some complex number which I know. So, from this I know that V has to have the following form, right. V has, so remember that if you write V as a linear combination of the basis elements, the coefficients are nothing but its inner product with those basis elements, right, because it is orthonormal. And so, we know that it had better equal this. So, we know that this is f EI bar EI. So, if at all there is a V, that V had better be this fellow. So, if it exists, it is unique, that is sort of what we have, this tells us, but we also know if it exists what it must equal, it must be this particular fellow, and it is now just a question of checking that this choice actually works. Okay. So, in a sense this is all rough column computation. So, this is all sort of things we will do in the margin and then sort of pretend we were very clever to begin with and just say what your V has to be, right. So, let EI be an orthonormal basis of V, we just say choose V to be this particular special vector, then just a question of checking, okay, and the checking is what we have really already done. So then VEI is FEI bar, and so EIV is FEI for all I, and we are done. Okay. In particular, this means XV is Fx for all x and v. Okay. And that is because I have proved that this is true for all basis vectors, therefore it is automatically true for all vectors just by linearity. It is enough to prove for basis. Okay. So this is just the proof, and it is more or less what we saw intuitively in this example. Any linear functional pretty much has this form, right? There will be the coefficients x1 and the coordinates x1, x2, x3 will all have some coefficients in front of them, and those coefficients you pull them together, think of it as your vector v. That is more or less what the proof is saying. Okay. So this is not a very deep statement, but it is a very important point of view, okay, and this particular theorem is called the Rees representation theorem. For a finite dimensional case it is not a big deal, but this theorem actually holds in far greater generality even in certain infinite dimensional settings, okay, and it becomes in the context of Hilbert spaces and so on. So it is a very important theorem. In finite dimensions, like I said, it is not a big deal. Okay. So this is a slight detour. Our eventual goal is to try and define what the adjoint of an operator means. Okay, and to do that we are going to use this Rees representation theorem. Okay, so what is the adjoint of an operator? So what is it that I will construct? The adjoint is the following object. Okay, so given an operator A from a finite dimensional inner product space V to another inner product space W. So I have an inner product on V and I have an inner product on W. Maybe to prevent confusion, let me just put subscript V and subscript W, because I am going to use the same symbol on both. So there is an inner product on V, there is an inner product on W, both of them are finite dimensional spaces, finite dimensional inner product spaces. Okay. Now what is the adjoint? The theorem says the following: given a linear operator A from V to W, there exists a unique linear operator in the reverse direction called the adjoint. Okay, maybe I should not use A, let me call it T, because A is psychologically a matrix, T is psychologically an operator, at least for me. Okay, so there is a linear operator which goes in the reverse direction with the following property, satisfying such that what happens. So let me draw this picture. So I have got V and W, so I take a vector V in V and I take a vector W in W. What can I do to them? A is supposed to move in the forward direction, right? So I can apply T, I apply T to V, and what is this operator T star? What can I do to it? I can act it on W and I get something in V, right? So I have taken one on each side, V here, W there. I have applied T to this and I have applied T star to that. Okay. So what is my claim? There exists a unique linear operator T star with the following property, that the inner product of V with T star W, okay, I take inner product of V with T star W, this inner product I have taken V, equals the inner product of TV with W, and this inner product I take in W. Okay. So think of this as a theorem if you wish, theorem definition. Theorem says, given any linear operator between two finite dimensional inner product spaces, there exists a unique linear operator going in the reverse direction which satisfies a certain inner product equation. Okay, what is that equation? For any pair of vectors, so this is for all vectors V in V and W. For any pair of vectors V and W, one from each side, T acting on this and T star acting on this will give you 4 vectors in all. take the two vectors on the left hand side, take their inner product, that should equal the inner product of the two vectors on the right hand side. Okay. So, this is the theorem. So, firstly let us show that such a thing actually exists, that one can construct such an operator always, and this operator, given it exists, it is called the adjoint of T. So, let us first prove. So, before that, any questions on the formalism itself? This is what adjoint means at an abstract level of operators. So, let us prove that such an operator always exists. Okay. So, proof. Okay, so let us look at the right hand side. So, what I am going to do is I am going to fix, so remember I am fixing, okay, I do not need to fix everything, let me fix W alone for now. Let me fix a vector W in W and do the following. From V to W I have got the operator T. So, any vector I will map it to TV, call it X. So, take an vector X in V, it maps to Tx, and from W I have got a linear functional. Okay. So, what is the linear functional going to do? It is just going to take inner product with my W. So, remember I have fixed a certain W. So, this guy is some linear functional. Sorry, what? Huh? W will be X.
Tx, comma X.
No.
Because it's a linear function.
It's a linear function.
It's a linear function. Okay, I have fixed my W. Sorry, what is the question?
Because both has the same field.
Alright.
So, but it has same field. Both has the
See,
same
both are about the same field, yes. Clear orthogonals.
Dimension also
Doesn't matter. One can be some m dimensional, other can be n dimensional. Yes. In practice, all those situations will arise. Okay. So this is clear what I can see. What is given to me data? I only have T. That's all is given to me. I have to work with that T. So what I am saying is fix a W. First, I am going to fix that W. When I fix a W, then I automatically get a linear functional on W. Okay. What is that linear functional going to do? Take any vector, it will map that vector to y comma w, right. So, this Tx is something I put in because I am saying it's a composition. So, let's do this. Let me do this first. See, given any vector y in W, consider the linear functional which takes inner product of that vector y with W. So, you agree this is a linear functional? This is exactly the functional we talked about before, right. So, fixing second component as something, and this just for definiteness, let us remember where the inner product is happening. So, if I have y, then inner product of y with W, the inner product being in W. So, this is a linear function that I will get because I fixed a W. Now, let me also do one more thing. Let me look at the previous step. So, I am going to now take a map from V to W. So, I take a map from V to W. What is this map? It takes my vector x. So, this is just my given linear operator T. It maps x to Tx. Okay. So, I have two linear functions. So, I have two linear maps, one from V to W, another from W to F, and when I have two linear maps and I compose them, the answer is still linear, right. So, the composition of these two linear maps continues to be a linear map, okay, but now it is a linear map from V to F. So, let me compose these maps. So, what is the composition going to look like? So, composition will now be x maps to Tx, Tx will go to inner product of Tx with my fixed element W. So, this overall guy is a linear functional, inner product. Okay, it is an element of V star. Okay. Now, what did Rees representation theorem tell us? It said if you have a linear functional on your vector space, on a finite dimensional inner product space, corresponding to that linear functional there exists a unique vector in your vector space. Okay. So, now I am going to apply Rees representation theorem for this linear functional. It therefore tells me there exists a unique vector. So, there exists a unique what shall we call it, V in V, such that this linear functional is nothing but, it's the same as, so let's just write such that this linear functional x going to txw coincides with the linear functional x going to xv, right. This is what Rees representation theorem says. If you somehow manufacture some crazy linear functional, there will be a vector v in your vector space such that that linear functional equals taking inner product with v, okay, that equals that other linear function. So these two linear functionals are equal. In other words, for every x in v, tx comma w, inner product in w is the same as x comma v, inner product in v. Okay, there is a unique vector. This is for given any, this is true for all x, right, for all x in v. Okay, now what does this tell me? This kind of tells me now what I should define T star as. Okay, so now we say, okay, how did that v come about? It came because I have fixed my w, right. So I will now say, okay, this w I will map to this v. This is okay, this chain of, it's slightly confusing chain of reasoning, but finally what I have done is I had v to w, I fixed an element w in w, and then I did a bunch of strange things, and at the end of it I was able to manufacture an element v in v. Okay, so I was able to, corresponding to this w, I was able to somehow get a vector here, okay, and that vector I want to define as the T star, my image of w. Okay, so this vector v that we manufactured we will call T star. Okay, now if you do that, then observe that the equation, this equation here becomes exactly the sort of equation we had earlier. Therefore, Tx comma w equals x comma T star w. This is true for all x in v, and of course now I can vary w also. For every w I have uniquely found an image v, right, and it is also true for all w in w. For every w there will be somebody called T star w. This is okay. Okay, so it's I mean the first time you see it, it's always somewhat confusing, so I would recommend sort of looking at it a few times. But what the Rees representation theorem finally does is it proves the existence of this map called T star, okay, which satisfies this very interesting equation. Okay, the thing that I have not proved is that the map is linear. I just know that it is some function, that's all. Right? We have managed to construct, for every w we found some v, but why should it be true that if I take w1 plus w2 the answer should become v1 plus v2? Why should the image also break up as a sum of two things? So linearity is something that one will have to show. Okay, so maybe we will just show linearity. So let us prove that this map that we have constructed here is linear. Okay, and that is just going to come from this uniqueness. This uniqueness is very important. Okay, so let's prove it. So if we now have, so claim is T star is linear. Okay, let me just show additivity and leave the scalar multiplication.
Is it not that the map that we have constructed from x to f, I'm sorry, v to f, that was automatically linear?
That was
For
linear.
every
Yes.
for every x we have the corresponding T star.
Correct. If you change x as x1 plus x2, this tx comma w will become tx1 comma w plus tx2 comma w. That is correct.
That doesn't prove that it's linear automatically.
That doesn't prove this, because what I am saying is if I change w as w1 plus w2, corresponding to w I somehow associated in an indirect fashion, I got a v, right, somehow, I am saying if I change W as W1 plus W2, the V that I will generate will also be the sum of the two V's.
But at the end, we are mapping to this linear functional only.
This side, this equation.
No, the left side we have the second. That composition only we are mapping it.
That composition is the left hand side, correct.
That is already linear.
That composition is linear in X, also linear in W.
So I want it linear in V.
Yeah, so we want to see what happens to that composition when we change W linearly. That's basic. But you are right, that's exactly what we are going to use now.
So how you know that, how you can define, what is the guarantee of the existence of T star? The define T star of W equals...
T star is just a function. At the moment, I am not saying it's a linear transformation.
No sir, I am asking, how you know that such a T star is existing?
Such a T star means what T star?
So you are saying that define T star of W equal to V.
Correct.
But we know that from the reducibility theorem, if you have the functional, I can correspond to one element, I can get it.
I can find a unique V corresponding to that function.
Yes, but how one V, if some V will be there means it's mapped with onto is how it's possible. T star of W equal to, such a T star how you exist, you take it. What is the guarantee of T star W equal to V?
See, W I fixed to begin with, V I manufactured. Right? If you start with the W, you can manufacture a V, correct? Unique V. I am saying now define a function, not linear at all, just some function from W to V as follows. Start with the element small w, whatever V you manufacture, that V is the image. I define just some function, random function at this point. T star is just a name of my function. Is that alright for now? That function, if I define like this, it certainly satisfies this property. It satisfies my inner product equation for sure, because that's how I got it, right? By applying the manufacturing process was so that this equation will be satisfied. That was the idea of the manufacturer, right? The thing now is that how are you sure you have done it in a linear fashion? Why does this strange function that you have constructed, why should it be linear? That is not clear a priori. Okay, but let's prove it, because the function has this property, right? So what property did it have? Tx comma w or tv comma w is v comma t star w. Okay, this is in w and this is in v. Now my question is, what happens if I change w as w1 plus w2, right? So let's try that. If I change w as w1 plus w2, tv comma w1 plus w2 is, so I want to know why t star of w1 plus w2 is the sum, right? But on this side I know tv w1, see I know linearity also in the second variable, right? My inner product happens to be linear also in the second variable. So let me use that linearity. So the left hand side splits into two pieces. But then what is this? This is v comma t star w1. This is v comma t star w2. So what have I shown? That these two guys are equal. In other words, v comma t star w1 plus t star w2 I have shown is the same as v comma t star of w1 plus w2, correct? I have just done it. I know the crux of the matter is this equation, that this guy splits into two pieces, and now this is true for every v. Okay, the inner product of v with something is equal to the inner product of v with something else, and this is true for every v, means those two guys have to be equal to each other, right? Why is that true? What's proof? If Vx equals Vy for all v, I claim that means x equals y.
We can write it like that, v comma x minus y equals to 0.
V comma x minus y is equal to 0 and put v equals x minus y, right? This is the standard proof, right? So you would just take v comma x minus y is 0 and then put v equals x minus y, and that will tell you that this is 0. Okay, so that's basically the proof here, that finally shows that t star w1 plus t star w2 is t star of w1 plus w2, and likewise you can show the scalar multiplication also. Okay, so this is the abstract definition of the adjoint. Now So the thing to keep in mind is the following. I mean, there is a certain sort of way in which one plays with it. So what we are really doing is there is this operator t, and it's as if when you move it to the other side. So one tends to imagine it as follows: I've got a t, and when I try to move the t to the other side, it goes and sits there as t star. Okay, it becomes a different operator. If you attempt to move the t from the left side to the right side, you can do it, except you have to replace t by this different operator called t star. Okay. So in particular, t star star is t. So observe that
Just one more flip will give you this.
will give you back this. So let's show that t star star is t. So observe that this original equation that's there, that can be rewritten as follows. So let me interchange so I write this as w comma tv bar. That's the left hand side. Right hand side also I will change the order, t star w comma v bar. Right? Both will come with bars. So all I have done is taken this given equation and just swap the two things like that. So it becomes bars, and of course if both are equal with bars, they are also equal without bars. I can take bar on both sides. Okay, but now look at the thing on the right. Think of t star itself as my operator, right? T star is my operator. So now the same thing as before. What will t star ka star mean? If I try to move the t star from the left side to the right side, it will become its star. Right? That should be, by the same theorem that we did, for t star there should exist somebody called t star star, right? Its adjoint, which satisfies this inner product equation. But now you compare these two equations. This says w inner product t v is equal to w inner product t double star v, and this is true for all w. So the same logic that we applied before tells us that t double star and t are actually the same. Okay, so this is the thing with the adjoint. Now let's just do some examples to get a sense of what this looks like, and to sort of see why why it's useful sometimes to think in terms of this abstract definition. The example I am going to take is not going to be our usual Rn or Cn. Okay, so I am going to do the following. I am going to take my vector space, my inner product space, to be the space of polynomials. So here's my definition: f is a polynomial of degree less than equal to n, and the additional condition also going to this f of 0 equals f of 1. So remember we talked about the set of all continuous functions on 0 1. So C01 is, let's say, all continuous real valued functions. Okay, so you take the vector space of continuous real valued functions on 0 1. That's of course an infinite dimensional vector space, right? Inside that infinite dimensional vector space, I am going to consider the following finite dimensional vector space, which is only take polynomials of degree less than or equal to something, and there is an additional condition I am putting, that f0 and f1. So if you draw the graph of this, on 0 and 1 it takes the same value, something like that, right? So it's got the same value at both places. Okay, so we'll see in a minute why I want all this. So this is some finite dimensional vector space for sure, because space of polynomials of some degree itself is finite dimensional, right? And this is some additional constraint, f0 equals f1. Okay, and it's a subspace, because if I add two things or subtract, or multiply by a scalar, this condition will also continue to be true, that f0 will always be f1. Okay, now why am I doing this? Because I am going to define a certain linear operator on V. Okay, so I am going to take the derivative. So I take polynomials of some bounded degree with this property, that f0 equals f1, and then I compute the derivative of this guy. Okay, so already I am just starting to see some trouble here. The derivative should continue to satisfy that property as well, right? So maybe I should also,
C dash.
yeah, I should just ensure that that condition is also true on the derivatives. So let's just put some additional conditions here, just to ensure that I'm going to be, it's closed under this operation. So let's put a bunch of zeros maybe that's easier. So f of 0 equals f of 1, f dash of 0, f dash of 1 are all 0. Suppose we do that. Okay, now why am I doing this? So what I am saying basically is that at 0 and 1 it takes the value 0. Further, the derivatives are also 0. So derivatives are 0 means something like this, right? Here also derivative 0. Or it can go up and down and so on, but at the two ends I want the derivatives to be 0 also. It's fine. So I am just doing this just so that it's my operator is well defined, that's all, not for any great reason. So let me see whether this now makes sense. So I should call this, let's call this f dash of x. See, all this would actually be easier if we were just working in the infinite dimensional setting directly, but since we sort of doing stuff in finite dimensions, we have to tweak definitions a little bit to ensure everything's all right. Okay, so let's take the derivative function. Okay, so let's check. Firstly, it's a linear operator, right? Derivative is linear. F plus g, derivative will become f prime plus g prime. If f is polynomial degree at most n, derivative surely has 1 less degree, so surely it's okay. Now let's check this, because f0, f1, f prime blah blah are all 0. Oh no, then again I am in trouble, no? So the next guy will also have to be 0. Okay, can I salvage this? I need all derivatives to be 0. All derivatives at that point are 0. So some sort of C infinity thing. Will that give me any interesting examples? Not if it's a polynomial, right? Okay, no, I don't think I can fix this. Okay, so let me think about this just a little bit. So this condition is giving me some grief. So we'll come back to this example. So let me do the second setting, which is the case of matrices. Okay, let's do R3 first. So suppose I take R3 to R3. So R3 standard inner product, and I take the linear operator which does the following. Suppose I take xyz, which goes to, let me just move everything one step to the right in a cyclical fashion. So I have zxy, okay. So I moved everything one step to the right, and now I want to understand what the t star looks like. So my question is, what is t star? And let's just do this using the definition itself. What is t star? By definition, I take tv comma w, it should give me v comma t star w. Okay. So if I take v as my xyz, for example, and w as some abc, so what is tv comma w? So tv just means x, y and z have all been moved by one step to the right. So tv will be zxy, so its inner product with abc will give me az bx plus cy, correct. So think of it as abc are where they are, xyz have all moved one step to the right. So this is my left hand side. My right hand side is, so my question is, what should t star w be? So this is nothing but v is my xyz, what should t star w be, so that the answer matches my thing on the left. should be BCA, that is, I now think of it as the same guy, I rewrite it with XYZ coming first, right, it is X into B, C into Y, E into Z. So, the XYZ I imagine they are in place, but now the coefficients I move around, right. So, the coefficients are now BCA. So, what really happened in this? So, if I move on my left hand side XYZ, they all moved cyclically one step to the right. What happened to the ABCs? They moved one step to the left, right. So, these moved to the right, they moved one step to the left, and when you do that you end up getting this inner product correctly matching. So, let us do one more. Let us take matrices. So, if my vector space V is the set of all n cross n real matrices, and recall we had a inner product. What is the inner product? AB, should I call it AB or XY, maybe XY, equals trace of XY transpose, right. This is the standard inner product, in fact, trace of XY transpose. Now, let me define an operator T from V to V as follows. So, I will fix some matrix A, fix a matrix A, n cross n, and consider the operation which is left multiplication by A. Okay. Given X, send X to the product of A with X, that is some other n cross n matrix, alright. Now, the inner product is trace of XY transpose. Okay. So, now my question is this, what is T star in this case? Okay, the linear operator definition is clear, it just maps X to X. What does T star do? So, let us use the definition again. So, what is the definition? It is TV comma W is V comma T star W. Okay. Now, TV, let us see what is V is, let us take V to be X and W to be Y. There are no matrices, right. Remember, the vector space is now different, it is space of matrices. So, what is TV? TV is just A into X, A multiplied by X. This is a product of two n cross n matrices, by the way. So, now let us compute the left hand side. Left hand side is inner product. So, it is trace of Ax into Y, W is Y, correct. So, that is my left hand side. Right hand side, I know this should look like trace of, thank you, Y transpose, Ax into Y transpose. The right hand side should look like trace of, so the V is now just X, right. So, it is trace of X into what? I should be able to find this what here, that is what my T star will be, right. So, how do I massage what is on the left hand side to bring it to that? Okay, what property of trace are we going to use? Right, you can cyclically permute, if you have multiple things in trace, you can cyclically permute them, right. Trace of AB is trace of BA. So, I have trace of AX Y transpose, I will push the A to the other side, so that I have something which looks like this. So, it is now X Y transpose A, okay, but that is still not of the right form. Remember, I need it as trace of something called transpose, only then it is inner product, right. So, I need to rewrite this further as trace of X into A transpose Y the whole transpose, right. See, Y transpose A is actually A transpose Y car transpose, alright. So, therefore, what is T star? T star acting on Y is actually multiplication by A transpose, okay. So, see, this is already a situation where the vector space is not our usual Rn sort of thing, right, it is some vector space, the space of matrices. Okay, so let me come back and do the first one. So, I am slightly mystified by this additional thing that I need. but let's at least do it heuristically. Maybe I will not, maybe that will be something to figure out during the tutorial. So let's not worry about this condition for the moment. So I just want, ideally I would have wanted to just look at polynomials of degree at most n, and let me take the derivative operator. Okay, now let's see what our inner product will be. So firstly, what is the thing? If I take inner product TV comma W, so V is my function f, my polynomial f, W is my polynomial g. Okay, so now I look at TV comma W inner product, which is, I want that to equal V comma T star W. Okay, now what is the inner product in this case? Inner product is integral, no? The inner product was integral f of x g of x dx. So I have to do integral now. But what do I have to do? Integral of TV and W. So TV is what? F prime. So this is actually integral f prime x gx dx. Now on the right hand side, in order to figure out what is T star, I should somehow massage this integral to look like this, f of x into something dx. If I do that, then that something is my T star W, correct? Something involving g basically. So how will I do that? Integral f prime x gx dx, I want to make that f prime go away and be an f.
So we can replace f prime of x by integration 0 to x.
Sorry, what?
We can replace this f prime of x by integration 0 to x f x dx. So
Integration by parts we apply means minus. Integration by parts we apply means minus times that one.
Integration by parts, for example, right? So let's do integration by parts. So what will that give you?
But the boundary time says the problem.
That was all what caused me so much grief. So let's do this. So it is integration by parts will just tell me, see, this is u dv, right? Gx into derivative of f. So it is uv, which is fx gx at the two limits minus integral of
So then we use the compensable.
sorry, what?
Then we want to use the additional conditions compensable.
Correct. So I somehow wanted the first thing to become a 0. So f of, yeah, see, f of 0 and f of 1 are both 0, same g of 1, g 0 is 0. So I can do that. Then of course my first term will become a 0 if I make that additional assumption. The trouble is that that space is not closed under my derivative operator. If I take a function which satisfies, which is 0 at the two limits, then I take the derivative operator, then it's not clear that that will have that property, right?
We take compensable.
So I should do something like that, but then polynomial of degree n will become an issue. I have to ensure that. So maybe the correct thing to do is not to look at polynomials, but rather some continuous C infinity functions or something like that which vanish at those at the ends. Okay, so I don't quite know at this point how to fix it. I need to think about it a little bit, but let's just for the moment pretend that if I were able to fix this correctly, my goal is to say, okay, see, that limit I don't want to worry about. Fx gx, they are 0 at the end, suppose. Then the question is, then have I solved my problem? What is T star? So what should I put here so that the equation is satisfied? Minus g prime, right? So in a sense, modulo being able to fix this, what we are saying is that T star g is actually minus g prime, right? So in a sense it's like, this is sort of what the adjoint operation always does. It takes, there is some action, some operator t on the first component, the first vector, and there is some inner product. What you somehow want is to transform it, right? You want to keep the first vector as it is and do something instead to the second vector, and by doing that you want the inner product equation to be satisfied. So this sort of integration by parts is exactly, it correctly captures that philosophy. The other case which does that is this n cross n real matrices. You somehow want to think of this Ax this thing that A is multiplying the first guy, you somehow want to remove that and do some action on the second fellow instead and still get the inner product to be equal. So what we have done here is sort of use some trace property and remove the A from there, push the A to the second component, but when you do that some transformation happens, which in this case is transpose. So this is broadly what the A star does. Now there are sort of several other properties of A star, so we won't necessarily go into all of them. The key is however this property here, which I will write out, AB whole star is B star A star. Okay, so there are many other things as well. If I take a sum of two, I should call it S and T. So if I have S plus T cos star, it is S star plus T star. If I multiply by a scalar, then the scalar comes out as bar. So these are properties which are easy to remember if you think of them as matrices. See, the conjugate transpose operation has all these properties, right? So I mean in a sense, so does this, the operator version. And okay, so all these properties are true, and maybe I will leave these as something for the tutorial as well. Now let us see where, so finally, so here is the key thing, how is all this related to the notion of conjugate transpose. So that is how I began, right, by saying on the one hand there is a familiar notion of conjugate transpose of a matrix, and that is what we call adjoint. Now here is this some strange way of talking about adjoints of operators. It turns out that these two match up once you convert the operator to a matrix using an orthonormal basis. Okay, so there is a twist here, you cannot just convert it using any basis theorem. Let T be an operator from V to W, and let you have to take two bases B and B prime be orthonormal bases of V and W. Then if you write the matrix of T with respect to this pair of bases, right. So remember, if I have two different vector spaces, then I need two bases in order to construct a matrix, one for this and one for that. So the matrix of T with respect to a pair of orthonormal bases turns out to be, I mean, to have the following property. So what is the comparison? If I likewise I can look at the matrix of T star. So remember, T star goes in the opposite direction, so T goes like this, T star comes in the opposite direction. T star with respect to B prime comma B, right, with respect to the other pair, turns out that that matrix is the same as this matrix conjugate transpose. So this is finally the relationship between the two notions. The matrix of T star is the conjugate transpose of the matrix of T. Okay, but only if I write both of them with respect to orthonormal bases. If I write them with respect to other bases, then this fact is not true. Okay, there won't be any easy relation between their two matrices. Okay, so maybe again let me not prove this statement, again not too difficult to prove, but let me get to my main point, which is why did we really launch into this general notion of adjoints and so on, because I want to talk about projections. So I want to sort of answer a question which I posed when talking about general projections versus orthogonal projections. So here is my theorem. See, V is a finite dimensional product space and I have two subspaces W1 and W2. Okay, so consider the projection, let P be the projection onto W1 along W2. Okay, so here's this is the general projection, right, it projects onto W1 along W2, then P is an orthogonal projection. So recall, what does that mean? What does it mean to say P is an orthogonal projection? Right, but that's my thing in terms of W1 and W2. Right, W2 is W1 perp or W1 is W2 perp. That's what it means for orthogonal. Right? The two spaces are perpendicular to each other. If and only if P is equal to P star. Okay, so the adjoint plays a role here. It sort of detects. So P being equal to its adjoint is the same as saying that the two subspaces that you began with are actually perpendicular to each other. Okay, so this is where adjoints come into play when you are talking about projections. So let us prove this statement. It's very easy to prove. So here's proof. Let's prove both directions. Suppose P is an orthogonal projection. Okay, so suppose W1 is in fact perpendicular to W2. So if rather I should say if W1 is equal to W2 perp, what we will do is we will just take an orthonormal. So we have to show that P is equal to P star, right. So let us do one thing, let us take an orthonormal basis S of W1, let's call it S1 of W1 and S2 of W2. So you take an orthonormal basis of each of these two spaces. Okay. Now what we will do is, so we have to show that P equals P star. What does that mean? I have to show Px comma y. So I want to show it is x comma, I mean I know it is x comma P star y, but what I have to show is that it is x comma Py. That is when it will prove that P is equal to P star, right. So to show P equals P star, I must show that this equation is true, and I want to show this is true for all vectors x and y in my vector space V, but it is enough to establish it for all possible basis vectors. Right. If I show it is true for all basis vectors, then of course it is true for all vectors just by linearity. So for basis vector, let us start by trying to establish it for my basis vectors. So I will just take this particular basis. So if we take all pairs x comma y in S1 union S2 and then try to show that these two sides are equal. Okay. So let us do this. We have to look at various cases. There are 4 cases, both x and y come from the S1, both come from S2 and so on. So let us do one of them. Case 1, x is in S1, y is in S1, they are both from S1, which means they are both orthonormal basis of W1. So then look at this, I apply P to x comma y, let us compute the left hand side. So what is P acting on x? X comes from S1. S1 is an orthonormal basis of W1. It will just be x itself, right, because a projection on W1 acts as identity. So Px is just x. So this is x comma y. And what is the left hand side? X acting on Py. Again y is also from S1. So Py is also y. So again it is equal to x. And so of course these are equal, right. So this is case 1. So let us do case 2. So I will do one more case and the others are easy. So let us do x belongs to S1, the other comes from S2. So let us compute what is Px comma y in this case. Well, Px is x as we said before. So this is x comma y, but I actually know something about x comma y. It is 0 because x is in S1 and y is in S2. They are orthogonal to each other was my assumption. Let us do the other side, x comma Py. What is Py in this case? Py is actually 0, right, because y is coming from S2, y is coming from the space W2 which is mapped to 0 under P. So in fact these are both 0, right. So they are actually 0 for 2 different reasons, but they are equal nevertheless. And likewise there are 2 more cases. So you also have to check case 3 and case 4. Okay, so I am just going to leave those two cases here. So what this essentially shows is that this property is true. And let us do the converse. The converse is even simpler. Converse says if P equals P star, then W1 is equal to W2 per. So if P equals P star, so let us prove this. What is W1? W1 was the range of P, W2 is the null space of P, right. So I have to claim that, let me prove that something in the range space is perpendicular to anything in the null space. I just have to show that these two spaces are perpendicular to each other. So let us take a vector in the range, let us take a vector in the null space and try to compute what is x comma y. Okay. Observe x is in the range, right. So that is an additional condition. What does that mean? X can be written as P of something, in fact it is P of itself, right. It is actually P of something, but that something can be chosen to be itself. X is equal to Px, so I can write this as Px comma y, but that means I can push the P to the other side and it becomes P star. But what is P star? By definition P star is P, I mean by what we are trying to prove, but then y is in the null space, so Py is 0, right. So notice it is a sort of a very neat sort of proof. You introduce a P because the left hand side is in the range, you push the P to the other side, it is still a P and it kills that vector y. So therefore x and y are perpendicular to each other, and that is what we need to show, right. W1 and W2 are perpendicular. So this being equal, P being equal to P star is sort of what distinguishes orthogonal projections from general projections. Okay. So if you remember, so let us just complete that picture that we talked about earlier. If you take idempotent operators, so the set of all P from V to V such that P square equals P, this collection in some sense is in bijection with complementary pairs of subspaces W1, W2, with the collection of these, right. This is the thing that we talked about, these two are really the same thing. And what is the bijection? Given a complementary pair, you associate to it the projection onto the first component. So idempotents are essentially like complementary pairs, but idempotents which are also self adjoint, so P star equal to P, so let us write like this. So if P equals P star, then we call P as self adjoint because it is equal to its own adjoint. Self adjoint idempotents are in fact if you wish, they are in bijection with subspaces of V, or we should really think of them as subspaces and their orthogonal complements. These are the complementary pairs we talk about. Okay. So these are, the bottom is all orthogonal projections, the top is all general projections. Okay. So this is the additional extra condition that we have. Okay. Now let us look at, still have some time. So let's apply some of these notions, the definition of adjoint and so on. Where we are eventually going is sort of to try and understand diagonalization of self adjoint operators and how it comes about just by looking at general properties of adjoints. So here is a little proposition on how adjoints. Okay, so T is an operator from V to V, so finite dimensional net product space. So if, so property 1, okay, so if T, if W is a subspace, so let W be a subspace of, if T maps W to itself, so it is what is called an invariant subspace, right. I have a subspace which T maps to itself, then T star the conjugate transformation. So, now observe the conjugate, I mean the adjoint will also be a map from V to V, right, because if it is from V to W then it is W to V, but here both are V, so it is again a map from V to V. So, the adjoint need not preserve W. So, if T preserves W, the adjoint need not preserve W in general, but the adjoint preserves W perp. So, for now let me only make this one statement. So, if T preserves a subspace W, the adjoint preserves the orthogonal complement. So, this is another important property of adjoints. Okay, so let's prove this. Question? Okay. So let's prove this. What should we prove? Let's pick an element W prime from W perp. We want to show that when you apply T star to that guy, the answer is also in W perp again, right, that T star preserves W perp. Now, what does it mean to say it belongs to W perp, i.e. we want to show T star W prime, its inner product with every W is 0. Right, it is perpendicular to everything in W, that is what we need to claim. Is all right? Okay, now as usual the standard thing we do with T star, we push the T star over to the other side, right, T star star is T in fact, and so when I push the T over to the other side, it becomes W prime comma T W. Now, what property did T have? T preserves W, right, the subspace W. So, what is T W? It is another element of W, that is all. This is some other element of W. This is an element of W perp, and so the inner product is of course 0 as required, all right. So, this is a very interesting statement. So, when I have adjoints, they behave in this very nice manner. If T preserves a certain subspace, I have a certain T invariant subspace, the perp of that subspace will become T star invariant. Is all right. See, all of these sorts of statements are actually much more natural to prove when you just think in terms of the operator definition of the adjoints. If you sort of work with the matrices, it is sort of much harder to make sense out of these things very easily, because then you must choose orthonormal bases of that subspace in order to convert that operator into a matrix and so on. Okay, so let us look at a very beautiful corollary of this simple statement that we just made. So, here is a theorem. It says, suppose V is a finite dimensional complex vector space, then there exists an orthonormal basis S of, okay, I should say, and T is an operator from V to V, then there exists an orthonormal basis, let's call it B, of V such that the matrix of T with respect to that orthonormal basis is upper triangular. Okay. So, this is sort of in the same spirit as the various diagonalization theorems one proves that given an operator it can be diagonalized, right. An operator which is sufficiently nice, you can diagonalize it. This is an upper triangularizability statement. It says given any operator, we do not care what operator it is, on a finite dimensional complex vector space, you can always diagonalize it by passing to an appropriate orthonormal basis. Okay. Okay, so let's prove this, and the complex is important here. We need to have that it's a complex vector space. Now, how do we prove this? am just going to, it's just a simple application of the previous statement that if T leaves something invariant, T star leaves the orthogonal complement invariant. Okay, so let us do this. So consider the operator T star. I already have T, I am going to consider T star. It is a operator on a complex vector space. So we sort of know, eigenvalues, eigenvectors, characteristic polynomial, etc. Let us look at its characteristic polynomial. So look at the characteristic polynomial of T star. It is going to be some polynomial with of some degree n, but we are now working over the complex numbers. So that characteristic polynomial has at least one root, right? It in fact has all roots in the complex numbers. So it has at least one eigenvalue. That is basically our point. So if T star, so let me just write like this, T star has an eigenvalue. Because I am over the complex numbers. Now if I am over the real numbers, I can't say this, that is where the problem lies. So if I am over the complex numbers, T star has an eigenvalue, let me call it something lambda, and a corresponding eigenvector, right. So let me, if I have an eigenvalue lambda, then surely at least one eigenvector I have for that corresponding to that eigenvalue, and let V be an eigenvector. So look at that space. So let us define W as the span of that eigenvector. Okay. What can I say about T star acting on that subspace? It will again be subset of W. See, what does eigenvector mean? Eigenvector is just a one dimensional T invariant subspace, right. That is an eigenvector of T. Here I am doing T star. So an eigenvector of T star is nothing but a one dimensional T star invariant subspace. Okay. So now I can use my previous little proposition which says if a subspace is invariant under T star, its perp will be invariant under T, right. I am just replacing T with T star in this case, which implies by the previous proposition T of W perp is subset of W perp. Okay. Now what I will do is I will sort of so what has happened, the size of my problem has gone down by 1. If V had dimension n, let us look at this space W perp. What is its dimension? It is n minus 1, right, because my W has dimension 1 and so this guy has dimension n minus 1. Now what I will do is I will just restrict T to this subspace W perp. So now let's just do this once more. Now let's consider, instead of the full subspace, just restrict T to this subspace W perp. Okay, maybe I should call it something. Let's not call it W. So let's call this subspace as W sub n minus 1. Let me call it as this particular W perp. Okay, I have got an n minus 1 dimensional T invariant subspace. So that is my point here. So W n minus 1 is also T invariant. Okay, so therefore I will just restrict T to this. Think of it as now a new operator on a smaller dimensional space, right. Now again repeat the same argument. This is a new operator on some n minus 1 dimensional complex vector space. On this again same funda, there is some take T star that will have at least one eigenvector, that uska perp will be an n minus 2 dimensional T invariant subspace again, right. So by the same argument, now repeated with this guy, I mean you could also state this by induction. So by the same argument, there exists W n minus 2 smaller than W n minus 1, which is T invariant, and so on. So you keep going like this. right. So, what I finally managed to construct is I actually have a one dimensional subspace contained in a two dimensional subspace and so on. Dimension of Wi is I. Okay, I have got a flag of subspaces, but with the interesting property that every one of them is T invariant, such that T maps each of them to itself. Okay. So, this is how you construct a flag of T invariant subspaces of all dimensions. So, it is called a complete flag. Okay. And what we did is cleverly use T star at every point. You take an eigenvector of T star, that is a one dimensional space, its perp will give you something of one smaller dimension, which is T invariant and so on. Okay, it's all right. Now, this is the same as upper triangular reusability. Being able to find a complete flag like this is actually the same statement as upper triangular reusability. Okay, why? Because you can use this to construct an orthonormal basis of V in the following fashion. See, there is W1 which is one dimensional, so you take an orthonormal basis of that guy. Next, W2 is two dimensional, so there is one extra dimension, so you extend this orthonormal basis to an orthonormal basis of W2, right, Gram-Schmidt for example. So, you will find one more orthonormal basis. Now, you find another orthonormal basis, one extra guy in W3 which is not in this and so on. So, there exists an orthonormal basis E1, E2, En of V with the property that if you stop at the ith step E1, E2, Ei, it is an orthonormal basis of Wi for all I. How do you construct this? Step by step extending the basis, start with W1, extend to W2, extend to W3 and so on. So, you will actually construct a basis of the whole space which is compatible with this flag in some sense. Now, when you write T in this basis, so if you write the matrix of T with respect to this E1, E2, En, what will it look like? First, I am supposed to figure out what is T acting on E1, right. E1 is in W1, and when T acts on W1, the answer is again in W1, right. So, which means T E1 should be just some multiple of W1. So, this is just it's some multiple of E1 again. So, it is this and everything below it is 0. The next column is supposed to be T E2, E2 belongs to the space W2 and W2 is T invariant. So, when I act T on E2, it will be some linear combination of E1 and E2, but it will not involve any of the other E's. So, T E2 will involve E1 and E2, but none of the others. Likewise, T E3, because E3 is in W3, T E3 is only a linear combination of the first three basis vectors and so on. So, this is exactly upper triangular reusability. Okay, finding a flag of T invariant subspaces. Okay, so let us see. Okay, maybe this is a good place to stop. So, what I will start with next time is the diagonalization itself, and for that we need some additional property of T. So, the operators that will be useful to us, it also comes up in applications to data science, principal component analysis and so on, is the case of self adjoint operators. If T equals T star, then we can do better than what we have just done here. So, the beauty of this theorem is that it is completely general. It had absolutely no assumption, just any operator on a finite dimensional complex vector space. You can always orthonormally upper triangularize it using orthonormal basis. But when you have extra condition that T equals T star for example, then you can in fact diagonalize it, okay, and that is the, like I said, the important case. And what I will do next time is to also talk about some special what are called minimax properties of the eigenvalues, and they again play an important role in applications to data science. So, that is the plan for tomorrow. Okay, we will stop.
Any complex vector is always diagonalizable because of this.
Not diagonalizable, upper triangularizable. any complex matrix is upper triangular residue.
Sir, eigenvectors are linearly independent because the nth are
No, but why are there n eigenvectors? I don't have any.
Take the matrix.
No, sorry, what's your question again?
Suppose every time you are restricting one eigenvector you are finding. Suppose n by n matrix means n
Ah.
eigenvector you are getting.
No. The trouble is that is only to the restriction, right? See, it's a new operator. The restriction is, so you are now restricting t to that wn minus 1. I am not finding an eigenvector of t, right? I am restricting t to that space. See, what is restricting mean? Restricting is a slightly subtle thing. When I restrict t to wn minus 1 like this. So, sorry, so just say, tell me your argument again.
My argument is, suppose the matrix is diagonally separate, it has the nth n matrix means a linearly independent eigenvector must be there.
Why?
Then what is that's one. Whenever the matrix is diagonally separate,
If it is diagonally separate, it has n linearly independent.
so we are getting a linearly independent eigenvector.
Where are we getting n linearly independent eigenvectors? For t star, you are saying?
We are getting for restricted t.
It's not linear.
For t star, for example, is that what you are saying? See, for t star, so that's how the proof is proceeding. Right? So let's just analyze where the eigenvectors were produced. So first we said t star from, so let's do it for t star. It's okay, it doesn't matter. T star is also fine. So let's try and see whether this proof tells us that t star is diagonalizable or not. Right? That's your worry, that t star somehow it seems like in the proof somehow we have constructed n linearly independent eigenvectors of t star. So I claim that's not the case, but it's subtle. What you are saying is correct. So first step is alright, we found one eigenvector, correct. Second step is where there is a problem. Now what are we doing in the second step? We are restricting t to wn minus 1, right. Now what is t star? See, t preserves wn minus 1, but t star does not necessarily preserve wn minus 1. This is not true. I mean, we do not know it to be true in this case, right. We only know that t preserves wn minus 1. T star preserves the perp, but t need not preserve wn minus 1. So what will happen in general is, what you are saying here is, look at the operator t restricted wn minus 1. If you try to find the star of this operator, see how will the proof proceed next step? You are saying, okay, here is a new operator, I find its star. Its star will be some operator from wn minus 1, wn minus 1. That star operator will have an eigenvector, right, and then we go to the next step of the proof, and so on. So this operator that we have constructed is not the same as t star restricted to wn minus 1, because t star does not preserve wn minus 1 in general. So what will happen is the following: when t star acts on wn minus 1, the answer will go out of wn minus 1. It will give me some component which is in the ambient space. What this operator actually is the following: it is t star and then you must project onto wn minus 1. So that is what the thing looks like. I mean, I did not want to get into the full details, but essentially these two operators are not the same. So if you want to write an actual equation, it is the following: t restricted wn minus 1, the star operation is the following: you apply t star to wn minus 1, the answer will go out of wn minus 1, and then you project back to bring it back into wn minus 1. So p is the projection onto wn minus 1. Okay, so you add t star as before, but project the answer back to bring it into tn minus 1. So it is this new operator that you are actually constructing, and this new operator has an eigenvector again. Okay, then next step of the proof, you will construct yet another operator which is t star projected onto the wn minus 2, and that will have an eigenvector and so on. So the eigenvectors, you are right that eigenvectors are being constructed at every step of the proof, but they are all eigenvectors of different operators. First fellow is T star, second is P T star, P prime T star, and so on.
Real, suppose I take the real vector space means, then what is the assumption I want to change which to this kind of thing?
For reals you cannot do this because
something I will make
If
the
all the
assumption.
eigenvalues are exist, then you can.
correct. So if all your eigenvalues are real, for example, okay, if I have a real, I have a operator over the real numbers, and
T
I
star
know,
equal to I take it.
then you can actually do diagonalizability. So if you want to do upper triangularizability in the real case, then what you need, like I was saying, is all the eigenvalues should exist. They should all be real. If they are all real, then you can apply the same logic. Because all you want is that there should be at least one eigenvector. For one eigenvector, there should be one eigenvalue. That you are guaranteeing by your assumption.
Excuse me, sir.
Yeah, go ahead.
So W was being generated by an eigenvector. So that's why we could say that it was T star invariant directly.
Yes, correct.
Because eigenvector is one dimensional basically.
Yes.
That's why.
Yes, correct. Exactly.
And sir,
Yeah.
after that when we wrote that but following the same argument, so it means that we were having a guarantee that there will be more eigenvalues.
So what we are doing is we are constructing a new operator. So that is this. See, we are constructing the restriction of T to Wn minus 1. That is now a new operator on a, think of it as a new operator on a new vector space. And now that fellow will have a star, right? So that is this operator here. That new operator on that new vector space will have an adjoint, which is star. That guy will have an eigenvalue again. And now and then you repeat the argument like that. Yeah.
That top one what you wrote, T star, if it is preserved, then might be that my matrix should become diagonalizable.
Then it will become diagonalizable. Correct. Exactly. Yes. If T star preserves that, then you will get diagonalizability. Correct. No? Sorry, why? Tell me again.
But
If it is true.
If it is true, then it becomes diagonalizable. That the top condition what you wrote.
At every step, right?
At every step.
Correct. Because then it will also say that T, yes, because then it will say T preserves the perp. T preserves Wn minus 1 perp. So the eigenvalue that you pick for T star is actually also an eigenvalue of T, eigenvector of T. So it will probably make it self adjoint. No, it will not be self adjoint.
Nothing but diagonalizable.
It will become diagonalizable with that property. So it will become normal in general. That's the general theory, the structural theory.
So do we need orthogonalities for the triangulability?
Yes, it will produce an orthogonal.
But we can go with a normal basis also. We can get. Because if I take a vector from W1 and another vector from W2, then that vector, any element of W2 can be written as those two vectors, and I can put those elements along the column vector of the vector.
No, what is the statement you want to make? What is the statement of here?
We can take any basis vector to make the triangle, to matrix as a triangular matrix.
Yeah, sure. You can. I mean, you are saying the proof will be simpler if you allow for arbitrary basis. That word is? Yeah, correct. Yeah. I mean, there's a different proof of this. You can also prove it differently. That just looking at the quotient vector space. Okay, we'll stop here.